Welcome to this tutorial on biases in subjective quality tests. Now, as researchers in quality of experience, we are interested in finding out how people perceive multimedia services. For example, we want to know how much do people like a given service? How much are they annoyed by a video that just doesn't load? Of course, the overall goal is to make services better for everyone, but it's necessary to understand the human element as well. There are lots of factors that influence the way people perceive such services, and just making a good guess isn't proper research either. That's why we do subjective tests. So we get a bunch of people into a laboratory room and we show them a number of video clips or audio sequences, and we let them rate those to find out what their impression of the quality is. We observe how people react, we ask them some questions, and then look at the results in more detail. Now, there's a big distinction in the way you approach such a test. You could either do it qualitatively or quantitatively. A qualitative test refers to research that asks more about the why and how than just the pure numbers. It's about methods you would typically find in social sciences, consisting of interviews and observations. When you develop a new system, a qualitative test may actually help you in identifying the attributes that users develop to describe that system, and such explorative studies may actually help you find certain behavioral patterns that users tend to employ when they use the system. Quantitative results, on the other hand, are what QoE researchers know more about. It's about a number of ratings that you get for a certain stimulus, and we often use these ratings as ground truth to develop a so-called instrumental quality assessment model. Such a model, given an input stimulus, outputs the quality as perceived by a human being without a human involved. So it's nice for an automatic analysis of quality. The thing is that these models are typically trained on subjective tests, but those tests aren't just a necessary evil, they are actually more complicated than some people think they are, because it's not just about getting the data to train your model with. You know that the human is a very complex being. Humans are not machines. Everybody reacts differently. So everybody will be influenced by different factors during the test. And that's okay. We just need to be able to measure those factors effectively if we want to get good test results. The biggest challenge in designing subjective tests and conducting them is eliminating the factors that you cannot measure. We call those factors experimental biases, because those biases are present in almost any subjective test that you do. But before that, a word about what we actually want from tests. We want them to be both valid and reliable. Valid means that the results actually correspond to what you think they are. Are you measuring what you think you are? Did you ask the right question to your subjects? Did they understand the question at all? The real-world analogy of such a valid test is taking an arrow and shooting it right in the center of your target. Reliable means that your results are consistent. For example, when you do the exact same test twice, but on a different day, do you still get the same results? Or did the results vary completely? For example, because you did your test early in the morning and your subjects weren't quite alert? But it could also happen that within the same person's ratings there are inconsistencies. For example, when your test is too complicated, when it's not clear what you were asking them, and when people are overwhelmed by the test itself. The real-world equivalent would be always hitting the target in the same spot. What often happens in reality, though, is that people sometimes reliably hit the wrong targets or unreliably hit the right target. You want a compromise of those, and you want to design your tests properly to avoid this. There are different types of biases, and I want to briefly explain what they are and how to avoid them. Random biases are those variations that you see when you ask, let's say, 25 people to rate the same thing. That's expected, as everybody is different. Those are random biases, and there are some good ways to eliminate them. One of the most important ones being just asking a lot of people, because it makes your statistical significance higher. But there can also be systematic biases, which are consistent, repeatable offsets in your data. And these are much harder to find and combat, but some clever people have thought about this, and now we can at least be aware of them. Even more so, there are biases that are present anywhere in life. For example, when you are biased by the way the frame of your TV looks rather than the actual picture quality. At the same time, there are biases that are only present in the laboratory tests. And in this tutorial, we want to focus on these biases. Now, I have a big list of biases present in the lab. It's not something I invented. There is actually a nice publication by Sławomir Zielinski, and I really suggest you read this paper. He and his co-authors identified the following biases, which are quite a lot. Now, subjects, of course, don't always think about these biases and that they are susceptible to them, but that's beside the point. You should still try to eliminate all of them if you can. There are even some more biases that have to do with the way you as a test conductor influence your results. Those are generally called experimenter biases or observer expectancy effects. In this case, if you're interested in it, there's a nice classification from Sackett from the year 1979. And as you can see, they've come up with a lot of biases. And if you look closely, there's one that says looking for the pony. If you, like myself, don't know what that means, just skip to the end of the video and I'll explain why. Basically, what it means here is that the idea behind a test shouldn't be to just collect data and then find something in that data, but you should have a proper hypothesis before and don't just look through your results trying to find something significant in there. That's something that we also call p-hacking because it's about statistical significance, so don't do that. But let's get back to the actual problem of doing a test in the lab, and let's relate it to what subjects are doing there. The more you eliminate all the random biases from your environment, the more you end up restricting that environment to become something very artificial. To some extent, that's normal and expected, but you will find that now your results become much less ecologically valid. That means it's much harder to apply your results in real life, where conditions are quite different. At the end of the day, it's really a trade-off between a controlled environment in the lab and a very realistic test situation, maybe even at home. So we had this list of biases before. Here's now a brief overview of some of them. The first are appearance and expectation biases. I already hinted at this. We know that subjects rate differently when they know that they listen to a certain brand versus when the brand names are masked. For example, if you have a loudspeaker in the lab and you cover the name of the brand, people are going to rate it differently than if they know it's a loudspeaker from the brand XYZ. The same is valid for video. For example, are you watching sequences on an expensive TV, or is it a computer screen, or is the name of the TV hidden? So the rule is here to make the test as blind as possible, meaning figuratively in the sense that subjects don't know what they are exposed to. So don't tell your subjects exactly what codec are you using, what packet loss did you set. Don't tell them about the conditions that you apply for the tests that they take part in. Situational context is another big influencing bias. It could matter a lot where you actually do your tests. Are people watching videos at home or are they in the lab? There's no formula on how to evade this bias, but ideally you want to do the tests in different environments. We know that people tend to be a little bit more critical in the lab. That is when, for example, the lighting setup is less forgiving and the proper speakers are used, etc. Take that as a starting point, but be aware that there's no number to be applied here. Another bias is the recency effect. It explains when people rate something, they focus on the thing they last heard or saw, basically the last portions of a sequence. For example, if you play a video that has a really bad distortion right at the end, people are going to remember that more than the rest of the sequence, so they're going to rate it worse than they would have had they seen this distortion somewhere else in the sequence. Now, what can you do against that? Well, you should generally avoid to have very strong quality degradations right at the end of a sequence, unless you specifically want to investigate that. Also, you could, for example, just use shorter sequences so people will have the entire presentation in their memory when they rate it. But of course, sometimes you want to test longer sequences. In such a case, you could, for example, apply different degradation patterns over time So you could have the same kind of degradation at the end versus at the beginning to actually test how big is the influence of that recency effect. There are also some biases in the way people use rating scales. One of them is the contraction bias. It basically says that people tend to avoid using the extremes of a scale. They may actually relate their ratings to a center, so they pick a center point and then they only slightly deviate from that center, so they don't use the extremes of the rating scale points. That's also an expression of uncertainty. Typically this happens in a single stimulus test where people rate one sequence at a time and they don't have to compare it. If such a contraction bias happens, you actually may want to change your test to use a paired comparison where people always decide between two samples, for example. There could also be a bias due to a perceptually nonlinear scale. For example, when the scale that you're using implies that the labels are equidistant, but in the mind of people they are not. Equidistant means that the difference between the individual labels is the same no matter where you are on the scale. Now, you can help your subjects by actually adding numbers to that scale so that you suggest the equidistance between those labels. Lastly, a very important bias is the range equalization bias. Here, subjects tend to make use of the entire rating scale, irrespective of the actual range of quality that they saw in the test. Now, let's look at this figure to help you understand. We have two tests, both with similar content, but a little bit of different range of quality. Here, let's assume that we know the hypothetical quality of the stimuli already. In both of the tests, people will probably use the scale in the same extent, though in the first test, the quality range is much smaller, and in the second test, the quality range is much bigger. Still, people will probably use the entire scale to do their ratings. They equalize their rating range to whatever they saw. When you just look at the results of one test, this isn't a problem, but it also means that you cannot compare the results of two different tests if they showed a different range of quality. A good way to counteract this bias is, at least for a set of tests, to always show the same range of quality. Even better, you could take the same samples and use them across multiple tests. Usually you would pick the highest and lowest quality samples and maybe some in the middle and use them as quality anchors. So what's really important to stress here is that these biases relate to one thing. You cannot always compare one test with another that easily unless you know what kind of quality range has been shown or if the rating scale has even been the same. Also, if the situational context is different, it may impact your results. If people are in a different mood, same thing. If you show different contents and use a different scale, you cannot put all the results in one bowl. But enough for now. As you can see, there are so many biases, we don't have the time to go into each one individually. I can really recommend you read the paper from Zielinski, and if you want, you can also look at this huge list of other biases that I just showed before. Now, with regard to all these influencing factors, just remember that the way you design and conduct a test, and even the way you analyze the data, could have a big impact on your results. So just be aware of that. Thanks for watching, and check out some of the other QoE-Net videos as well. But wait, what's looking for the pony? Well, there's a modern fable. It's about a father with two sons. One of them is a pessimist and the other one is an optimist. And to make both of them a little less extreme in their view of the world, the father buys the pessimist a room full of toys. And for the optimist, he just gets a room full of horse crap. Some days later, he comes back to his sons and he finds that the pessimist is crying because his toys are all broken, or they're at least about to be. But when he goes to the optimist, he finds him very happily shoveling through all that horse manure, and the son says, "Hey, you know, there's so much crap around here, there must be a pony somewhere."